Okay. Okay. Can you see my screen on Zoom? Everything good? Cool. All right, so let's get started. This is Python for Physics. Quick overview of today. I'm going to give a brief introduction about myself. Then I'm going to do a pretty lengthy, in-depth lecture, which will hopefully take approximately an hour. And then once you guys are thoroughly confused, we'll take a break, and then I'll do some live examples, and then we're going to do the first project introduction. So there's a lot to do today. I like to have kind of more of a like open interactive class. So if you have a question, raise your hand or shout at me. Either one is fine. I know for Zoom people, just throw your questions in the chat. We have people monitoring it, so hopefully it'll get answered. So yeah, who am I? I'm Katie or Catherine. I go by both. I'm a fourth-year undergraduate here at Berkeley. I'm studying astrophysics and aerospace engineering. My experience with coding and all sorts of research and stuff. This is my third year teaching coding. I teach the Python decal, which has a link there, shameless plug. I'm also a software developer at Space Sciences Laboratory, which is up the hill, for helping with some NASA mission operations and the pipeline for that. So that's pretty fun. I've been an observational astronomer for 3 years. Those are some of the telescopes that I've had the pleasure of using. The big red one is the one that I use on a monthly basis, and the other two were just fun projects. Those are radio dishes. They're super, super fun to use. And then, yeah, I have a career interest in instrumentation, which means I like the bridge between software and hardware. So I like building the telescopes and finding everything out so that people can use them to actually collect data. Aside from that, I also like building rockets. I've participated in a lot of amateur rocketry here at Berkeley. So just basically all things space. Outside of academics, I love food, love coffee. I know, super unique. I'm probably way too active and qualify as a gym bro, which is unfortunate. And I do like touching grass when I have the time. And I have photo evidence of me at Yosemite, which is kind of performative, but yeah. So moving on. Let's get into the programming bit. If you guys have any questions or anything about like research or like Berkeley or whatever, I'm happy to yap. Catch me afterwards. I can't do it with the online people, but go to that link that I saw and you can learn more about what I do. So yeah, more about programming. What is programming? It's basically just developing instructions that your computer can understand. So computers and people do not speak the same language. So we have coding languages that are basically interpreters between English or whatever language that you speak and whatever language the computer speaks. So each coding language is slightly different and it has its own strengths. So just like our languages that have different characters, different grammar, same thing for coding languages. But once you kind of get the gist of it, it's easier to pick up a different language. So specifically for this class, Python is a high-level interpretive programming language. So what does that mean? High level basically means it's easy to understand if you speak English. There's a lot of intuitive words in it. And it's also interpretive, which means that it needs an interpreter between the code and the computer. And you can see on the diagram that a compiled code just goes from the coding language or your language, it compiles it, which goes into machine code, and then it runs your code. But an interpreted code has to go from the coding language, runs the code, then interprets it, needs a virtual machine, and then it goes into machine code. So basically you can think of it as like compiled code is basically the entire thing is converted into the machine code at once, and then it's run. But the interpreted language is essentially like you have a scribe there and it's writing it line by line, and that's how your code is read into your computer. So they're slightly different, they have different strengths, but for the purpose of that, that's just what Python is. Compiling code examples are like C, C++, and interpreted code is like Python, JavaScript, etc. We're only focusing on Python, so don't worry about it. I just wanted to give some background on what's the difference and why we chose Python. It's mostly easy and it's used everywhere now in a lot of different science fields. So yeah. So where can you code with Python? There's a ton of different coding platforms available for free. There's your terminal, which is the top left. That's the Windows logo. It might look slightly different on Mac, but overall the same. It's called the same thing. That's on all of your devices. That is how you directly communicate with your computer. You can type into it. It makes you look like a scary hacker. It's probably really intimidating right now, and unfortunately, we don't have enough time to cover that in the class, but you should know what it is. Anaconda is another, like, it's kind of like Google, where you can have like Google Drive, Google Docs, a bunch of different things. There's a lot of fun stuff in there. If you want to learn more about programming, look into it. VS Code, that is the Google Docs of coding editing. You have to download that one, but that one is really good because it gives you a ton of fun colors. It gives you the red squiggly line if you typed in something wrong, which is really common and really useful. Yeah, really good editor. That next colorful symbol is Git Bash. Git Bash is another really helpful way of editing code. It's just another program that you can use with GitHub if you're familiar with that, which is just an online cloud for coding. Jupyter Notebook is really similar to Google Colab that we saw last class. They are basically notebooks, which just means that you have specific cells of code. The difference between VS Code and Jupyter is that usually in VS Code, you have one big text file and you click run and it runs the entire thing. With notebooks, you can run one cell at a time and you can break up your code into chunks, which means that you can run one loop, for example, and you don't have to run your entire 1,000 lines of code, which is really useful for debugging and testing code. Like I said before, Google Colab is the program that we're going to use for this course. I just wanted to make you guys aware of things that you'll probably see in the future if you continue with programming. And yeah, like anything else, different programs have different strengths. So moving on to brief computer structure. Again, all of this like introductory stuff is mostly things that I just want you guys to know about so that you're not confused later on after this course. We're not really going to go over much of the computer structure and deal with that, but I don't want you guys to be scared of the files because I was scared of opening my files for like 18 years of my life. So they're organized in group structures called directories, which is basically just a folder. They can contain more directories, they can contain files, they basically hold everything. So all you need to know is that directory is folder. That's just jargon that we use in coding. Directories and folders can contain basically all your files. So if you look to the tree on the right, you have your little icon. The folder is for Mac and the little finder guy is, I'm sorry, the folder is for Windows and the little finder icon is for Mac. Basically, once you click on that, you're in some sort of directory. From there, you can go into another folder, and then you can go into a file. So the default directory is called your home directory. So that's whatever you open up into in your terminal. And more jargon, upstream means it's above or below. So in this case, to the right, the parent directory would be upstream of the folder and upstream of the file. So those are called the parent directories, like I said, and they're the parent directory to everything held within it. So even the file, the parent directory would be the one that's labeled parent directory. For this case, it would be something like Python for physics, and then your folder would be like, I don't know, day 2, and then your file would be an example that we're going to go over. All of these directories and everything, this path on the right with the arrows to get to the file is called a file path. That's essentially one line of code that tells your computer exactly where a file is. So if you rename something, you're just renaming that path. It's not really changing anything. Does that make sense? Like you're not physically moving the file, you're just telling the computer to look to a different spot. So an important note to make also, a file cannot be accessed through any shortcuts. It has to go through that same path. You cannot come from a different parent directory and like make a shortcut and skip this parent directory and folder and go straight into this file. So it's like Russian nesting dolls. Like you cannot get to the center one without going through all of the other ones. Are we cool on that? That's really important. Like I said, we're not going to go over this, but important that you understand this. Any questions so far? Am I going too fast? Okay, cool. So let's get into the basics. Syntax. It's basically coding, spelling, and grammar. It's the overall structure of code. So anytime we say syntax, a syntax error is a typo. It's one of the most common reasons and also one of the most infuriating reasons. But yeah, if you don't know the syntax, you cannot code the same way that if you don't know the grammar or if you don't know the spelling or words of a language, you can't speak the language. You're not fluent in it. So an example of this would be if we are trying to do a print statement like Yvonne did in the last lecture, we're going to do the print, which is the call to our function. Print is a function that is automatically in Python. And then we have our string, and strings are always surrounded by quotation marks. I'm going to go over this in a second. So that's our string syntax. And then inside, it doesn't really matter what you put in there. No matter what, it's going to be printed, even if it's gibberish. So going on to variables, which would be something that's inside a string. So to create a variable in Python, you basically assign a value to a variable. So like x equals 5. So it functions really similar to how we assign variables in math, but whatever is on the left will always be assigned to the right. You can't put an equation on the left side and then equal it to x. Python gets really confused and it'll not be happy and it'll give you an error. So the variable essentially just holds information in Python, very similar to math variables. So if you're saying x equals hello world, which is our entire string, and then you print x, that is the exact same thing as saying print hello world. It's just that you can do other things with x now because it's a variable and it's a little bit faster to code later. Really useful for math. So moving on to data types, which is what a string is. It is the classification of a data variable. So common data types are strings, integers, floats, etc. Those are the three most common ones. A string is a word that's surrounded by quotation marks or apostrophes. So that's what we saw with hello world. An integer is any whole number, specifically a whole number. 1, 2, 10, 1 million, and 5 doesn't matter. It just has to be a whole number. A float is any number with a decimal, which is the same thing. If there's a decimal anywhere in the number, it is a float. So you can see there's a couple of examples. 0.1 is like super normal. 0.002 doesn't matter that there's not a 0 in front of it, still a float. Even if you have 100,000, if there's a decimal at the end of it, it is a float. You can convert between data types with functions, but we're not going to get into that right now. So that's just to let you know. There are data types and data structures, which some of them are data types and some of them aren't. It's a little bit confusing, but for the most part, they're the same thing. But it's basically a format that can store more than one variable or entry of data. And the common data structure types are lists, tuples, dictionaries, etc. I'm going to go over the first two right now. Lists. This is probably the most common one, and really, really valuable. It's just a collection of items stored in a single variable. So like if you see at the bottom there, it says fruits. Fruits is my variable. That's one word. And then you can see it's equal to the list on the right, which is denoted by square brackets. Lists are ordered. So there's an index that always starts from 0 and goes 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. You can access that and those elements within the list. That will be covered later, but just to let you know, they are ordered, they are changeable. So you can change, say if I wanted to put cherry in front of banana, I could do that. That's important to note because it really helps you if you're doing math. If you have a list of student names and you want them in alphabetical order, you can rearrange it in a list. You cannot do that with a tuple. Tuples are unchangeable. They're extremely similar, but they are noted with a parentheses instead of a square bracket. And you can have the same thing. So if I have weather, sunny, partly cloudy, rainy, I can't change that. I have to make an entirely new tuple or list or something that I can change it if I want to reorder those or whatever I want to do, but it is not changeable. It's ordered in the same way that you can access it in lists. So if I wanted to pull this information from this tuple and put it into a list in the same order, I could. Any questions so far? Yeah.
What's the benefit of using the tuples as a business?
Probably just that if you don't want something changed, I default to lists. Yeah, they're easier. And like later when you get more advanced, NumPy arrays are significantly easier because they function as a matrix. And if you don't know what a matrix is, that's fine. But they're easier because they are set up to do math easier. So yeah, we'll get into that later. But yeah, that's the benefit. So yeah.
Wait, so if you like put those three values into your list or your tuple, and you like enter out of your variables, can you like not change everything?
Yeah, you can't change this tuple, like or tuple. Your like weather tuple, right, would not be weather. You would have to set it as like a new variable, or you would have to reset it to weather as a different tuple, but they would technically be different. So like you cannot change it, you just have to create a new one. So if you want information data that's like taken once and you're not going to change it, you're not going to reorder it, it needs to stay in that order, you can do it as tuple. But like I said, generally I usually just always use lists. It's just like the common thing. I don't think I've ever used a tuple when I code. It's just good to know what it is. I'm not gonna go over dictionaries. Google it. I don't have enough time, sorry. So let's go over a quick data types example. What would the data type of the printed statement this be? You can just say it. Yes, it would be a string. Strings always have the quotation marks, and it has to be consistent. It's either apostrophes or it's either quotation marks. You can't do a quotation mark and an apostrophe. Python yells at you. You just can't do it. So pick one and stick to it. I like apostrophes. It genuinely doesn't matter. So moving on to functions. Functions are reusable code that are extremely similar to math functions. You have an input and you have an output. The way the functions are structured is you have a defining statement. So that's the blue def, which stands for define. And then you have your function name, which in this case would be exponent. You want to use descriptive names so that if you're working on a coding project and say you have 2,000 lines of code, which does happen, you don't want to come back to it 2 months later and be like, why in the world is my function just named F? Like, what does that stand for? How am I supposed to know that that stands for function? So just write out function or exponent or whatever the purpose of it is, so that when you call it back later, like the print statement, it wouldn't be as useful if I just had P as the function name. It's like significantly more helpful if I say print. So this is the same thing. So you have exponent, and then you have your input variables, which are X and Y. And then you have a colon, and every time you hit enter and you're in a Python environment, it should automatically indent for you. But if it doesn't, you need to have that indent. Otherwise, Python doesn't read it, doesn't read the lines of code after it as inside the function. So then your function ends and you get an error because it thinks that there's nothing in it and you don't have a return statement to end your function. So you can put whatever you want in the middle of it. In this case, I'm just doing exponent. The two asterisks next to each other, that's the exponent or power symbol in Python. So that means that z is equivalent to raising x to the y power. Yeah, that's basically it. And then you have a return statement. So that just returns whatever you want, and that says, hey, my function is done. That's what it's going to spit out. That doesn't necessarily mean it's going to print it. So if you make a function and you're like, why is it not printing my output? You need to put print instead of return, or return print z. Do you have a question?
Yeah. Is print a function?
Print is a function. Yeah.
You need to write def in front of it.
No, not when you're calling it. But if you're making the print function, then yes. I'll cover this in a second. Are we good with the structure? Any questions with this? Don't forget the colon, really common mistake and hard to spot. So moving on to comments and coding etiquette. This is something that I think a few of you had questions on before. Comments are marked with a hashtag before the commented out code. So everything after the hashtag in that specific line is essentially invisible to your code when you run it. So it doesn't matter if you put 2 + 2, which Python will usually calculate as 4. It doesn't matter what you put after that. You can put anything you want. It will not read it. Comments are really helpful for describing your code. They're also really helpful for debugging. So if I'm printing in a loop and I don't know where the loop is going wrong, I can print, right? If I have a loop that's counting down from 10 to 0 and it's skipping and it's only doing every other letter, I can put a print statement to try to see where it's going wrong or where it's removing those. So it's really helpful to be able to quickly comment those out and not have to rewrite the code or print every single time. You just get lazy when you code. Coders are kind of lazy in the same way that mathematicians are kind of lazy. That's why we use like Vim and stuff, because it's faster. So yeah, comments are really, really crucial for good coding etiquette. And I'm such a stickler about this because, again, if you have a project that you worked on 2 months ago, this happened to me this year, then you don't have good enough comments. You're really confused when you come back. And that's really terrible if you're doing research. So please, please, please put comments in your code. It's really helpful to you. It's really helpful if you're collaborating with people. And yeah, that's all I have to say about that for this one. So the example in this case would be your function. That's going to be the same one from earlier, but instead of having just a function that says, just the plain code, I'm saying this function returns x to the y power. In case somebody doesn't know what the double asterisk does, it seems pretty intuitive now that I say it's raising x to the y power. I go, yeah, okay, z is equal to x. That must be the power symbol. And then I'm returning z. Are we good? Cool. So I'm going to continue harping on good coding etiquette. Please have good coding etiquette. That includes using descriptive variable names, commenting your logic flow. Logic is basically just your thinking. They call it logic in coding because why not? Describing the purpose of functions. So like this example, having a description after that. Those are also called doc strings, by the way. If you have a comment underneath your function, you have a doc string, and that's by 3 quotation marks. So if you see that, don't freak out. It's just a description. And then consistent syntax, coding style, and spacing. What in the world is coding style? You can see on this, I changed this, the way I typed it a little bit with this function. You see how here, everything has nice even spacing? If you have inconsistent spacing, it gets really weird to read. It's like walking up stairs that are different steps. Like it's hard, or different heights. Like it's really hard to read, and it's not nice to people who are reading your code, which is usually yourself, so be kind to yourself. A better example of this would be even spacing, better variable names. So instead of saying x and y, I now have base and exponent. So my product is going to be the base to the power of the exponent, and that's going to return my product. That's a good function. I'm happy with that. It could be even better if there was a comment saying what it did, but this is better for now. Any questions on that? Awesome. Let's take a 10-minute break real quick. I'm going faster than I thought I would, so that just means we get to do more examples, but yeah, hang out for a couple minutes. If you have any questions, come ask me. Yeah. I'll go over that. Okay, is there like a specific stuff they want? Okay, yeah.
Send me the software
Okay. I'll recap. Yeah. And I'll go to. Yeah. Okay, awesome. Yeah, I figured like it was. I think I just saw a comment that said, if a tuple is an unchangeable object, why can you change a list inside a tuple? And your list is still a separate entity. So if your list is equivalent to, say, a number, so in this case, it's index 0, and the example that you gave, I think this was, sorry, I don't know how to pronounce your name. I don't want to say it wrong. But basically, if your tuple is a list that's 1 and 2, and your next entry is index 1, which is 3, you can still change your list in index 0, but you can't change the fact that that's a like list in your tuple. Like it's still taking up the same space. I hope that makes sense, because a list is a changeable thing, but you can't change an index because it's just like that single object. So like your object in the first index is an integer, and your object in the first one is a list, and you can inherently change lists, but you can't change the integer because the tuple takes that as changing. I hope that helps and answers that question. If it doesn't make sense, I'm happy to talk about it more. Just send it again, but yeah.
There's no reason.
Might be this year. About saying event, like.
Yeah.
I'm just gonna answer some of the questions in the chat verbally, to help out with some of the instructors, but. Or the TAs, sorry, but print is a function that is automatically embedded into Python. So. Like packages that we mentioned earlier, like numpy or matplotlib.pyplot. Print is something that automatically comes in the language of Python. So it is a function that will automatically print if you call it. I'm gonna go over this in a second, calling functions so that you can actually use them later. But P won't work because Python doesn't know what P means unless you set it to something or you define it as a function yourself. But print is basically one that was already created and Python already knows it. So yeah, that's why it's important to type print and not like print or crit or something like that, because Python doesn't know what those are, but it knows what print is. And yeah, there are other, I guess, like keywords, they're just functions. There are already like pre-programmed functions, I guess. There's so many. I will try to cover some right now. I'm gonna do a live code example, so. Like,
So you go to your, like.
there's another question in here. Okay, I'm just answering questions from the chat right now, which I guess is a good learning moment for everyone, so I'll cut the break short a tad bit. I'm sorry. I'll give you another tiny little break if I'm fighting for time later. But I answered 2 questions. One of them was really good. I don't have board space, but it was actually I need board space. Thank you. It was basically saying, hopefully you guys can see this. It was saying if you have a tuple and you name tough, right? And you have it equivalent to something here, and your list is 1, 2, and then you have a comma, and then your second entry is 3. I was saying that this is index 0 and this is index 1, and inherently this object is a list. And inherently this object is an integer. So if you have a list, you can inherently change this, right? List, changeable, tuple, unchangeable. So if I change the list and this is called my list. And the reason why we do this in Python is because, like I said, like print, there are certain commands and functions in here where if I say list, it reads it as list and it's thinking I'm trying to change something to list. And so you cannot set this function, which is list, you cannot set list equal to some list because it reads this and goes, wait a minute, this is incorrect syntax. There's no parentheses here. I can't do this. But if I put my list, it doesn't read this as list. And now I can do this. Does that make sense? Okay, awesome. So yeah, there are certain keywords like this in Python, and you basically just figure it out as you go. They kind of highlight, or you'll get an error and it says add improper syntax. You can go Google it and go, what in the world is add? What in the world is list? And what does it do? And then you know to avoid it for later. So a lot of trial and error. I like, there's literally not enough hours in the day, and also I don't know the entire language of Python. You just learn it as you go. So if we have my list, and that's equal to 1, 2, we can change my list to whatever I want. If I want to change it to 0, 0, sorry. If I change this to 0, 0, and this is above tuple, then automatically my list is set as 0, 0, and it reads that into it. So it's as a variable. So this is just like represented as x, but the tuple reads it the same either way. Does that make sense? Okay, awesome. I forgot what the next question I answered was, but I think another really good one was is like return, similar to print. Return is a command. Print is a function that is automatically in Python. So print with any function. I'm going to go over this again for online people if you can't see this, but print is a function and you're calling it as a function. So somewhere in the Python language, you have def. Print, and somebody put the code to say, when somebody calls print, do this. So it has some return statement somewhere, whatever. Some brilliant little coder did this a million years ago. When now we want to print something, we have print, and we say hi. And this is called calling a function. So whatever you put inside the parentheses is how you call your function. Similarly, if you're running a script and you're going, I wrote this, but like this is some function that you did that's like really complicated and awesome, right? You're saying I did this, why is it not printing or returning? You didn't call your function. Your function is only going to print and do this if you tell it to call your function. So if this is a different name, let's do something less confusing than print. If we have a function called, you can't call it add because Python has add as a function in it. So we'll call it addition because we're unique. So we'll call it addition. And we're going to hope and pray that that is not a keyword in Python. So we're going to find our addition, and it's going to be like C equals A plus B, and then return C. If we want to do, and this takes in A, B, you don't have to type this every time, but it's useful to know which input variables you have. So if we're going to call it later, we're going to do addition. And then A and B, I don't know, 2 plus 4. And then Python is going to print, that's like notation that says you're in a Python environment. It's going to output and say that 2 plus 4 returns 6. This is how you call your function. Does that make sense? Okay, epic. Online people, did you see that? Hopefully. I'll code it again. Python right now. But yeah, that's a good question. Return, I hope it's clear now that return and a function are inherently very different. Return is a command telling Python to do something. Print is a function. Awesome. Okay. What do we have going on? Okay. Some more background before I do some examples, just so that you guys are a little more clear on what we're doing. Yeah. Yes, sorry. Okay. Yeah, most mathematical operations, like you would type it in a Google Doc or whatever, are the same that you would have in Python. So addition is the plus sign, subtraction minus sign, multiplication is the asterisk, the little star. Division is going to be the forward slash, and then the equal sign assigns a variable, which is kind of a weird thing to say instead of just saying it's equivalent. But you cannot have two sides of an equation in Python, it'll give you an error. So if you have I don't know, 1/2 mv squared on the left side, and you have 1/2 mv squared at v2 on the right side. You can't do that, it gives you an error. So this cannot do. Python doesn't like it. But if you were doing, if you set a variable and you say kinetic energy, 1/2 mv squared, we'll do 2. This is fine, and you can call KE later. You good on that? Another note on variables, you can reassign variables. So if I say K equals 1/2 mv squared, and then I say KE equals 7, and then I print KE, what do I get? Yeah, it reassigns. So you get 7, this one, the latest one, which means that you can have global and local variables. So if you have a function and you have a variable inside your function, so you have def, whatever, and I say my variable KE for some calculation that I'm doing in this definition is going to be 7, and then I have my return, and I say KE equals 1/2 mv squared up here, and then I print KE again down here. What do you think I would get? Yeah, you get 1/2 mv squared because this is a local and this is a global, which just basically means that this is accessible everywhere in your script or notebook, and this is only accessible and used inside your function. So this reassigns it every single time because Python is an interpretive script. So it reads it top down and it says, this is the first one, great. I'm doing this function, never mind, KE is reassigned, and then outside of the function, it's global again. Yeah. That's if you're calling it later. I think sometimes if you do call it and you run this and this is later, then it does technically reassign it if you're returning KE, because you basically put in one KE and then you spit out another KE and now it's global. But if you want it to be global inside of a function, there's a command or a keyword, if you want to call it that, that says global, and you put that in front of KE, and then now it's global and you can access it later. So that's just a helpful understanding for functions. Yeah.
When you have a variable like KE, does it have to be like 1 letter or 2 letters or other letters?
No. So going back to this, you see how it says exponent and product base? As long as there's no space or anything and it's all together, you can have a variable name. That's why a lot of people for variables, if you've ever seen it, although if not, it'll say like my underscore list. That's like one style. This is what I mean by like coding style. You can do my list, you can do my list, you can do capital M because Python is case sensitive, so you can do my list with a capital M and a capital L. You can do any variation of this, it just has to have no spaces.
And no like operations, like no dividing or subtracting.
Yeah, it has to be like one, like just contained like word almost. Python needs to read it as one object. Any other questions?
When cadence to another is going, you have to define the data type program.
No, so the data type is inherent. Let's do a live coding example. I'll go over some of this stuff. Is there like any popular question online right now?
What is very used about like the structure of a function?
Okay.
Like returning.
Got it. I'll go back to it again. So just so that you guys know, I'm gonna show you how to open up a Google Colab on your own. If you want to follow along with this, you can. I think it'll be posted later in the Google Drive. But we're gonna do Google Colab. It's the first one. You can open it on any browser. I'm not even on Google right now. I'm on Bing. We can do new notebook. Awesome. I have a new notebook. We can code. So I think this is automatically in Python. So we're gonna run with, yeah. See where it says IPYNB at the top? That stands for IPython notebook. Just so you know. So we're gonna call it functions, because we're gonna do a lot with functions right now. So general structure, if I want to write a function we'll do a really simple one. We'll call it addition. You don't need a function for this because like you can do 2 + 2 in Python and hit Shift Enter to run your cell. Or you can click this guy right here if Shift Enter doesn't work for you, but I'm lazy and it's faster. Yeah, so 2 + 2 gives you 4. With variables, if I set x equals to 4 + 2, let's see if it prints. No, nothing. So if I go to a new line and I put x, then it automatically prints the last line of whatever you do. But if I just put x in a new cell, it runs it. If I do print x, it also prints it. But if I reassign it, like what I was saying earlier, and I say x is equal to, yeah, we could do x + 2. Now it doesn't print anything. It doesn't get the last one. You have to write the actual variable itself if you want it to print at the end. And now it's going to give me 8 because x + 2. So you can do recursive stuff like this. Python keeps track of it. That's basically saying I'm assigning the value x, which at the start of this part of the equation is 6, and then I'm adding 2 to it. So now it's 8, and then I'm reassigning that value 8 to x. Does that make sense? So it's a little bit weird to see stuff like this, like x equals x + 2, but that's how Python reads it. Okay, as far as functions go, any ideas for a fun function?
Do an average.
Average? Oh yeah, we can do an average. So we can do def average. That's our first line. So def, remember, is called define. Average is going to be the name of our function. Oh, look, it gives you it there. And then you need the parentheses, and then it's going to take in some value. And since we know about lists, we can say my list, and with the underscore, it's going to be considered one entity. So we're going to do 1, 5, 10, 24, and -2. Python also understands negative numbers, which is very convenient. And we're going to do def average, and what we want to take in is going to be my list. And then from there, we're basically just gonna, would you need a for loop for this? I think so.
Oh, for a list?
Or can you use the average function? There's an average function. This is what I mean. There's probably a function for everything that you need in Python. This is why I don't live code, and I usually have code backed up. Or I think it out. I want to say that's a function. We're gonna call it average list. Okay, so what I just did there. I know there's functions for, do you know if there's an average function?
If you import NumPy, there's.
Oh, that's what I'm missing. Okay. Yeah, import your functions always. That's like the first thing that I always code. Is import NumPy. Oh. Import NumPy is NP. NumPy stands for NumberPython. NP is because we're lazy. Awesome. And then run the cell. You have to run it for it to import. And then I think you can do numpy.average. Yes.
It's NumPy.me.
Is it numpy.mean?
I think it's both. It's like redundant.
Yeah, okay. And then return average list. And see, it already knows I'm gonna make a mistake. It wants me to print my function. So this is my function. It's not gonna print anything. And now I'm frustrated because my function is stupid and it doesn't print anything. Okay, so now we want to print. We'll go into the next cell and we'll say print average. Yeah, and then it wants me to, you can click tab if it gives you an automatic suggestion that you want it to print already. And then it's giving me a little red error there because I didn't close my parentheses. And now it should print it. So the average of that is 7.6. We following? Or is that too fast? So if we want to look at this closer, we can zoom in and we can separate this a little bit and we can go, okay, we have our defining statement. My function is called average, which is because it's averaging a list of numbers. And then it's taking in my list. We can get rid of this and it'll run. It should run usually, maybe not. We'll keep it in there. So we have the input variable, which is my list in this case. So we'll say input variable to average, which seems really obvious now, but later it might not be so obvious. So my list, we have colon, and then we have it indented here. Just click tab, it works. And then we set a variable to average called average list to our numpy.mean, and that's a command or like a function, right? So the way that you know that it's numpy.mean is because numpy is your package. So numpy package, and then it goes into a module, which is like a folder, or we'll use the correct jargon, which is directory. And then it goes into a file, and that file itself has a function. So that's the entire possible chain. In this case, we're going from numpy, which is our package, module, whatever you want to call it, and then we're immediately going into the function where we want it to do mean. So we're saying in numpy, that's why we do import numpy, because that's like a package, that's like a folder or directory basically that we're importing everything that's within it. So we have numpy, and then we have a file called mean. There's also median and a ton of other stuff. Numpy.sine, numpy.cosine, numpy, everything. So it's really fun. If you want to learn more about numpy, just look up numpy documentation. I'll put that in here so you guys remember. So yeah, that's a function. If you're ever confused about what's a function and a command, if it's got parentheses, it's a function. Do you have a question?
Like the first block you wrote average underscore list is equal to numpy on the my list. Is there any reasoning for having it as an average just making you are you like allowed to just leave it as np.b and then just put that into the print?
Yeah, so it's like a more efficient way of coding. You can say def, we'll call it better average. Well, we'll call it efficient. And then we'll put our usual parentheses and we'll say my list. And then we'll do, you can just do return average. Or no, you can just do return dot numpy.mean. Sorry, it's really hard to talk and type at the same time and make sense both on the computer and what's coming out of my mouth. I'm not good at it. Huh?
You got a typo right before your first parentheses.
Yeah, you're right. So yeah, it doesn't print anything, so I have to go into a new cell, or I'll just do it in this one. And I'll say print efficient average. And then we'll put my list. 7.6. So it works the same. Do you see?
Yeah.
I just have a huge habit of assigning it to a variable and then outputting the variable. It just makes sense in my brain. You're so welcome to code however you want. That's a totally valid way and probably more efficient too. So yeah.
Or this is like a long way to it. If like we are using np.mean, so that means already a function and the library. So can we not just directly use that?
Yep. I'm just giving an example of a function. You could recreate numpy.mean with a function that has a loop and indexes through every single value, adds them up, and then divides it by the length. We just didn't cover loop structure or anything yet, so I just wanted to keep it chill and not confuse you guys because I know this is already a lot. So yeah, you can totally do it that way. This is just an example.
Could you explain global and local variables again for people?
Oh, yeah. Okay, that's like not super important. I just got caught up with it, but I can go over that. So yeah, I can do the example that I did on the board again. So if we have, let's not use that one. So it does take more time to like make a pretty notebook. But significantly helpful for later. By just making a text box like this, you can go up here and there's a button that just says plus text. If you're trying to make a new cell, you can either do shift enter and that'll automatically do it in code. Or you can just go up here and do code. Okay, global and local variables. We'll do the example that I did on the board. So kinetic energy, KE, usually what it's abbreviated as. We'll do 1/2 times m times v squared. Let me pause. Because I typed that really fast. So like I said, 1/2, that's division. If you want to make sure that PEMDAS isn't weird, you can put parentheses around it. So we have 1/2 times m times v, and then the power symbol is the double asterisk, so v to the 2 to the power of 2 squared. Yeah.
Does it make a difference whether you put spaces in between the V and then the two asterisks?
No, it doesn't. That's coding style. I prefer to put spaces because the difference in oh gosh. The difference in this, my brain just doesn't like the first one. That's like really hard for me to read. Significantly easier to read the second one, in my opinion. You can do whatever you want. This is what I meant, just like be consistent. If you have spaces between everything, put spaces between everything. Don't like do it every other one because then it's even harder to read. So yeah, we have kinetic energy. Let's say that. Laptop's slow. Okay. So kinetic energy equals KE. KE 1/2 mv squared. If you don't know what that is, then look it up. It's just a usual equation in physics. Basically just saying the energy of a moving object, particle, whatever you have. So yeah, if we have KE and we want to define, we'll say energy as our function. We'll say energy and it takes in kinetic energy and it takes in potential energy. And we say potential energy is equal to 2. So this is a global variable because it's outside. And by outside, I mean it's not in a function, it's just in a cell. And this is a global variable. So if we have kinetic energy and yeah, it wants me to input that KE and PE is a local variable. I'm going to code like I did before, which is going to say total energy is going to be equal to KE plus PE. And now total energy is a local variable. This like has a AI thing that I don't think I turned off, which is like the suggesting thing. I don't recommend using AI. I know it's like probably easier, but like you guys are on summer break, so like, you know, it's uncomfortable. Learning is uncomfortable, but it's really beneficial. AI is really tempting and it's just kind of not good for your learning. If you care about learning, don't use it. Anyways, that's my spiel about AI. Or use it to check your answers. That's fine. Use it as a tool, not as something to learn for you. Anyways, so if we want to print this, we'll do print energy, and then we'll put in K. And PE. And then it should return, I didn't define my variables. So we'll set M as 2, and this will be in kilograms. And we'll set V equal to 5, and then we'll do meters per second. I think it's very, very useful to comment your units because we're doing physics, not just math, and it gets really confusing if you don't know what M and V are. It's just good coding etiquette, documentation. So now it says that my total energy is going to be 27 joules, watts, whatever. Are we following? So if I tried to call total energy here, let's see what happens. Yeah, it's not defined because it's within my function. Even though I'm returning total energy, it just doesn't understand it. The return of it is basically the output of the function, which is what it reads it as, not as an individual variable. But if I did global total energy after I sign it, now it's a global variable. and this is command. So, why is this saying that it's spelled wrong? Okay, so our total energy is now equal to kinetic energy plus potential energy. I set it as a global variable after I assigned it its value, and now I'm gonna return it, and then we're gonna print it and see what happens. So, yeah, okay, so I guess that's backwards. So global has to be before, so that Python knows what value the global variable has assigned to it. Okay, there you go. Does that make sense? So, I don't remember all of syntax all the time or all the rules of Python. I know a lot about Python, but every coder does not at any given moment know everything about Python and the specific syntax. It is okay to look things up. Like, that is how you learn to code. You go, I'm trying to do this thing. Is there a function for that? What's the documentation for a function? If your teacher says, hey, here's a hint, use this function. How does that work? Look up that function, Python documentation. It'll come up with the official documentation, look through it and try to understand it and try to use it. That's how you learn coding. Are there any questions with the global and local variable? Does this make sense? Okay. Are there any questions from online? Any examples that they weren't covered?
Someone wanted me to go back and review the steps. We didn't specify what steps of
The steps.
but I also said that they can review the report.
Yeah. I'll go back to the lecture slides now. Are you feeling good about all of this stuff up here? Functions, data types. Okay, speaking of functions and data types, let's go over data type functions. So if you want to know the type of something, I have a variable and it's called my variable. And it's actually, I'll say name equals Katie. And then something better would be making a list called staff. And it's Katie, Mac, Yvonne, Alejandra. I hope I spelled that right. Okay. Yeah, that's my list, right? And then I wanted to say type within that list. I can access the elements in the list, like I said, with thing called indexing. So each of these has an index. So it goes 0. Python always starts at 0. It's called 0 index. If your like alignment with something is ever off, check that you started at 0. So like 0 would be my name. So if I do staff and then brackets and then 0, and I run that, that's going to give me back Katie. So I've just accessed an element within a list. This is not in the slides, by the way. I'm sorry, but hopefully it'll be in the slides somewhere so you guys can review it, but we'll do it here. So if I do the same thing and I do 1, that's the second entry. That's map. Okay. Same thing if I do 3, Alejandra, and then if I do 4, error. Its index is out of range. But if I do -1, it gives me the last entry again. And same thing with the rest of them. You can do negative indexing. Now you have Yvonne. Does that make sense? Where you can go back. So that's really useful if you want to find the last value in an entry. If you were recording time and you want to go, what's my total time that I recorded for, and you're storing the values in a list, you can do list -1, you have your total time. Yeah.
Why would, if you're going backwards, why would 100 be 0?
Because my name is 0. So Katie is 0. So that's the origin. So it's like a number line. If you're going to the right, it's always positive. But if you want to go backwards, -1 is one step to the left and it loops, which means it's the last one. Any other questions?
I think there's actually a question that might be useful to that might have to do with that confusion between print and return. Which is, why is it that you can just write staff -2 and it prints out the value of that variable without you having to use staff -2 as an input for the print function? Why then you have to write print stuff?
Okay. That's an artifact of a notebook. Thank you. That's a really good question. I said this like super quickly earlier. That's an artifact of notebooks and like whatever you're coding on. So Google Colab, whatever, if you have a variable that is the last line of the cell that you are running, it will print it. So if it can print the last line of whatever your cell is, it will. So up here, you see how I did total energy? I did print energy and I called my function, and then I did total energy and it printed twice. That's because I had a print statement, but it also prints the last variable every single time. So if I put, if I called X again, it prints X instead of total energy because total energy is no longer the last variable in my cell. So hopefully that makes sense to whoever had that question, but good question, good catch. The reason this prints out specifically for staff is because, and that's like not a list, right? Like I'm not creating a new list that says staff is a list of -2. That's the syntax for indexing. So if I have the name of a pre-existing list and then I do square brackets and then a number in that and it's within the range, then that's an index. If I'm creating a list, it has to be the name of my list that I want equals to something with square brackets. So I could create like a my list that's equal to just empty brackets and it'll be an empty list. But if I call it and I say type, which is the original function that I started this whole spiel about for, type tells you what data type you have. So type tells what data type you have. Oh my goodness. So it tells you whatever the data type is of whatever is inside your parentheses. So in this case, if I want to do my list, it'll say list. If I do X, I think X was like 8. It says integer. If I set a new variable and I call it my number, and I set it to -0.4, and then I say my number, it's a float. Usually I think Python or Jupyter Notebooks output and it says class string. That's what it looks like, but class just means that's like the classification, that's the data type, it's a string. There's just like abbreviations. Yeah, any questions on that? So type is really, really useful. I know this is a really simple application of it, but type is extremely useful because if you're trying to do a bunch of numerical calculations and you have a big matrix, which I'll cover this. But if you have some really huge array, which is structured like a matrix, or you can think of it as a list inside of a list. So you have a numpy dot array, which is a function, so you need parentheses, but then an array functions like a list, so then you need brackets. So if you have numpy dot array, this is my array, you can say equal to my array equals numpy dot array. If I want an array, like you can have all sorts of sizes and shapes. But basically you can have an array that's like your starting bracket and you can have your ending bracket, and then you can have one row in here, 2 rows, let's see, 3 rows, and then 4 rows. Does that make sense? So now this is kind of structured like a matrix. And if you're not familiar with the matrix, it is usually written with like really big brackets or parentheses. And you basically have entries. So you have something here, you can say 0, 1, 2, 3. Where each one of these, it is going to be a column. So it has 4 columns up here, and then it has 3 rows. So this would be a 3x4 matrix. It goes rows and columns. Does that make sense? So this is essentially structured the same as here, where in your array, you can have 3 different lists and each of them have 4 entries. Does that make sense? I know I'm going really fast and this is like really new content. Sorry, I don't know if you guys could see that. Yeah.
I have a question, it's not related to this.
Yeah, go ahead.
Oh, I just wanted to double check for like the staff list, would Mac be like both one and negative?
Yeah.
Okay, and then for the previous, like kinetic energy one, if you wanted to add units on the end, like, is there a specific function that you use?
Yeah, there's this thing, I don't know if there's another one, but there's this thing called AstroPi, which is like NumPy, and you can multiply units by it. I should know the syntax for that, and I don't know it as well as I do. But yeah, there's like functions where I think it's like the opposite. You can do a number and then you can do dot AU or dot meters or dot kilograms, something like that, where you can tack on the unit and then the unit is attached to that number. Instead of commenting it, but commenting it is also fine. Yeah, I don't know if AstroPi actually does map with the units. Like, I don't know if you if you do the 1/2 mv squared, if it'll come back as like joules or watts, even though the inputs are meters and kilograms and, you know. Does that make sense? Okay.
So the one time one will be followed by sign, my array and the NumPy array, and I can use my array, like, it does more than NumPy array.
Sorry, I didn't hear the first part of that question. Are you saying like, if I say my array and then numpy dot array, like, will this function as an array?
Do you, do you have blurred background on for your Zoom?
I don't think so, no.
Okay, then it's just the camera.
Can people not see it? I can type it.
Yeah.
Okay, I can type it. So this is a variable, and so what I have on the board is my array equals numpy dot array, and then I have parentheses because numpy dot array is a function, and then inside that it needs brackets because it functions like a list. So an array basically is a list, but it has different operations, and I think this is going to be covered later in the course again, so I'm not going to get too much into this. This is just very similar to lists and like much more practical. So basically my array is the numpy array. Numpy dot array creates the array. Does that make sense? So I'm creating an empty array right here. I think if I do, I want to say if I do like 1 by 2 and then I print my array, it'll give me. Maybe not. I could be wrong. Okay, yeah, it doesn't like this. If I'm creating an array, you know what I mean? Like if I want to create an array that's like one row, like no, like 1 row by 2 columns.
But you need to fill it with something. You need to fill it with zeros, for example.
Can you fill it with zeros? But okay, I don't remember the syntax off the top of my head. I think we can try Alejandro or numpy dot zeros. Oh, okay. Numpy dot zeros gives you the shape. Okay, this is what I wanted. So numpy dot zeros is an array, and if you do that, and I comment everything else out, which, sorry, that was a quick command. I did control / on Mac. It might be command /. I'll put a note on that. Oh gosh, sorry, I can't type. Control + / to comment out a line that you're already on, and it also works for uncommenting. That's why you didn't see me go back and type that. Okay, so if you want to do numpy dot zeros.
Yeah, I can put it in a tuple. This shape is.
Got it. Sorry, I like never have to do this. So, yeah, so there's my array. It's 1 row by 2 columns. Does that make sense? So like when you create an array, you would put something in it usually. And you can either manually type it or you can fill it with whatever you want. There's commands for that, but I've already given you guys so much today. I don't want to keep adding to it. But yeah, numpy dot zeros is the same thing. It gives you an array full of zeros. Are we good on that, or was that confusing?
How do you know it's 1 row by 2 columns?
Good question. There's a function for that. You can do numpy dot shape. Let's set this to a variable. That's the reason I like setting things as variables, is because then I don't have to retype it every single time. We'll call it zeros. Or, yeah, we'll call zeros. And then we'll do numpy.shape of zeros. And numpy.shape returns a value, a tuple of rows and columns. So it's one row by two columns. But also you can look at it, when I print zeros, you can see that we only have one row here, and then we have two values. So it's two columns. Even though it's not separated by a comma, you can see that there's a space there. That's how arrays are read. And that's how you can do it. We can change this and we can do two rows and two columns.
So if you would left that as 2, 1, they have just done like 2 zeros like up and down.
Oh, that's not. Yes.
Okay,
And that's a really good way of thinking. When you're learning coding, I would highly suggest you guys just go into Google Colab, open up your new notebook, and just go to town. Just see what you can do and what you can create. See if you can create what's the maximum range of a array. I don't know. Will it go up to 100, 1,000? I don't know. So yeah, try to figure it out. Just mess around with it. That's honestly the best way at learning like preliminary coding and like the functions and stuff like that. Just look it up and just kind of play around with it. Okay, any questions so far? Okay, it looks like there was a bit of confusion with the indexing. I did not make a slide on this because I just didn't. So let's go over that really quickly. Oh. So we'll say indexing. Python is a zero index. Meaning it starts from zero. Always, all the time. That's just how it is. If we have my list, okay, let's use a better variable name. We'll call it scores. And then we have a list and it's like 44. We'll do it out of 50, like 35, 10, 50, 48. It's just off the top of my head, really does not matter. If we want to access part of that, the way you have index syntax is you have list name, and then you have brackets, and then you have index. And index is the number that you want within the list. So if I have a ghost list right here, the same list would be 0 index. This one is 1, 10 is 2, 50 is 3, 48 is 4, and 49 is 5. Now, if I did the same thing, but I wanted to do it backwards, this would be -1, -2, -3, -4, and -5. Is that a better visual representation? Does that make sense? So this is a normal index, and then this one is a negative index, which just means we're using negative numbers to access the information inside this list. So if we do scores and we want to see how the first person did on, I don't know, something that has a score, some test or something, we do 0 because 0 is always the first index. So it's always the first entry or AKA index, and we don't have to print it because it's a variable or like a value that's the last line of our cell. And now we know that it's 44. If we wanted to do scores in a different cell, we could, and we could also do -4, which is a lot easier to type it than it is to visually look at it and go, that's negative. That's the fourth from the last. Because if you have a list that has hundreds of elements, you don't want to look through that. It's going to take a long time to load it. It's easier to do this. Hopefully that cleared up some confusion about indexing. Any questions so far? No? Okay. I'm gonna go back to the slides. And we're gonna do some physics. Can I just get a show of hands real quick on who has taken physics before? Raise them up real high. Okay, so quite a few of us. That's totally fine. If you haven't taken physics before, hopefully I cover enough of this, but it will definitely need some review because it's a lot to learn. So. All right. Like I said, same thing with operators. There are more operators than this. Even though these are like the simple ones, there's more. Look it up if you're curious. There are some useful ones, but yeah, just for basics, that's all you need. So, a couple little background things on physics. The position is going to be the location of an object. That one is pretty standard. Displacement is going to be the difference vector between a starting position and an ending position. So a vector is defined as something that has a magnitude and a direction. So if you have some sort of plot, right, and you have a vector, it needs a starting position, so you can start at 0, 0, and then it also needs a magnitude, which is going to be like how long it is, and then it also needs a direction. So that'll be either be the ending point or some sort of degree, but it basically just says, how am I going to draw this thing? Is the easiest way to think of a vector is that you need to know how long it is and you need to know where it's going. So we use that for explaining where objects are going. And then the distance is going to be the total ground covered. So up here, I have a little number chart. We have the origin. Negative is going to be to the left, usually on an axis. So this is like my x-axis, and it's in meters. That's the other thing about physics. Nothing is ever just x and y. It's x in meters. What's the axis in y? Probably also meters. So always keep track of your units. Yeah. Yeah, so I have a little diagram here. Say you're on a track, right? And your starting position is at the green dot. Your ending position is at the red dot. Your vector would be your displacement vector, which is that blue arrow going from the starting position to the ending position. So that's a displacement vector. And then your distance is the red line where you ran around the entire track, because if you cut the track, then you're disqualified. That's not how tracks work. So your red line is the total distance that you travel if you were running. Does that make sense? Awesome. So that means if you started on a track and you come back to the exact same spot in the exact same lane, if your velocity is the total displacement, your total velocity is 0. If you start and end at the same spot. Okay. So if you're running on the track, your average speed is going to be the total distance traveled. So it'd be like the red line on this, divided by the total time elapsed. So say you're super fast and that took you 30 seconds, right? You're running a lap in 1 minute. That's a 4-minute mile. That's super fast. So that would be your average speed. Your total distance traveled, that's probably like 200 meters if it's like an American track, which is 400 meters. So quick math. There you go. There's your average speed. Average velocity is slightly different. You have your notation here for the bar, or like V bar, which is just average speed. That little line always just means average, which is going to be your displacement over the time elapsed. So that's that blue line here. So that's this total distance over delta t, which would be the same thing, which is like 30 seconds. So yeah, and that's probably significantly less. Like that's probably only like 5 or 6 meters, however wide a football field is. And then you have instantaneous velocity, which is your velocity at a specific moment in time. So that's going to be v is equal to the limit as delta t goes to 0 of delta t over, or delta x over delta t. If you're not familiar with limits, just know that it's the derivative of, so it's dx over dt. If you don't know calculus, then I would look that one up. Yeah. So, does that make sense for these guys? Nothing too confusing, hopefully. The background, a little bit of background on 2D kinematics. Kinematics is just physics word for studying the like motion of objects.
Right, just a little comment, and we will learn all of that calculus and stuff at the end of the lecture series, okay?
Fantastic, thank you.
Turn that light off.
Oh.
It's like harder to see that.
Awesome. So 2D kinematics, these are equations that essentially describe pretty simple motion. So that means we have two axes or 2 degrees of freedom. So that's usually your x-axis, which is in the horizontal direction, and then your y-axis, which is in the vertical direction. That's just pretty standard. To the right is positive, up is positive. So position as a function of time is usually given by that first equation. That's just a known equation. We're not going to drive it quite yet. And then the same thing for y, and then velocity as a function of time. It's a similar thing, just looks like the derivative of that. Does that make sense? Because the velocity is a derivative of the position as a function of time, which is this last equation. Does that make sense? Okay, awesome. And then this would be the equations that are specifically modified for like free fall parabolic motion, which is the example that we went over at the end of last class. So it's the y, and you can see that g is replacing a. So in this equation, you see that ay right here is divided by 2, and then t squared. Here it's g because that's the acceleration due to gravity. That's the only acceleration that's acting in the y direction. If we're ignoring drag due to air and any wind or anything, like we don't care about that. We just care about gravitational acceleration, and that's it. For x, if you throw something, usually you just have that like one initial acceleration, and if you're not counting that, and you're just counting the time that the instantaneous moment that a ball leaves your fingertips, then it no longer has an acceleration. It just has the velocity that you gave it from the initial acceleration, but we're not counting that. So it just has the starting velocity from when it leaves your fingertips, and it has that the entire time. So there's no acceleration on x, it's just going in the x direction at the same speed. Does that make sense? Any questions? I can draw that out if it's like kind of confusing. I'm sorry for the people online, I cannot make a graph of this fast enough. It's much easier if I do this on a board. Okay, so if I have some graph, there's you. You have a tennis ball, you're super strong, you're gonna throw it super far. At the very second that the ball leaves your hand is t equals 0. And we'll say that that's 0, x equals 0. I don't know, maybe, hopefully you can see that. So this is t equals 0 and x equals 0. And from here, we're also going to say that this is y equals 0. Sorry, this ended up being a confusing graph because I added the person, but we're going to have a parabola, and it's going to go up, 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 and it's going to slow down, and then it's going to come back right back down. And this is 0. This is the ground. Just bear with me, okay? This is 0. And so your velocity here, we'll say that you give it a velocity of like 30, or not 30, 10 meters per second. Which is like ish 30 miles an hour. It's like reasonable. So it's going in this direction, right? We have a vector. And if you take the vector, the velocity vector at any moment, it's going to be the slope to this. Because that's the derivative. So when you take a derivative of some slope and you want you take the derivative of some line at a specific point, it's going to give you the slope. We all recall this from calculus, hopefully. If you don't know this, we're going to cover it again. But yeah, so that's going to be your velocity at that specific moment. We'll call it v1. At the very top, it's gonna come to a halt. V is gonna be 0 at the top. We'll call that VA, which stands for apogee, which is just a fancy word to say it's the top. So VA is 0 because it has to go up. Your velocity is 0, it's not changing anymore. And it has to come back down, and V is increasing as it goes down. So I didn't do that bad. V is increasing after this point, and then before this point, it's decreasing because the acceleration is acting in the downwards direction, which is called gravity. Does that make sense? So if you do a projection of this, and you have all your velocities here, your velocity, which a projection is just breaking your vector into two different components. So if you have your velocity, we'll call this V1. That's your velocity vector. This is going to be your velocity vector, so V1 in the x direction only. So we only care about what this is doing in the x direction and the value of that in the x direction. So you can do the same thing for V1 in the y direction, which is going to be vertical. And that's just that I do this poorly, but that's just the vertical component of this. Everyone following? Okay, lovely. So Vx, if you had an acceleration vector, that's not changing. You are not accelerating at all in the x direction after this moment. So that's why these equations are simpler, and that's why they're easier to solve. Your y, however, has a negative value. So you can say g is a negative, or you can mark it as a, and it's just equal to 9.8 meters per second squared. That's what it is for Earth, usually. And that's what this guy is. So 32 feet per second squared. Any questions at all? I think they're, yeah, okay. Sorry, I forgot about this slide. This is a better drawing of what I just did on the board for the people who are online. It has literally everything that I was just saying, which is awesome. So yeah. Is that clear with the projections there where you have alpha? And if you have the angle of that, you can use cosine and theta to get the either recover the projections or recover the actual vector. Yeah.
So if you had like, if you were just thinking about like it moving in the x direction, would it just be like a line at the same exact speed the entire time?
Yes. Yeah, because you're not accelerating, you're not decelerating. Yeah. The difference in the y acceleration is kind of this little diagram to the right. That's like your y projection, where you're just like, you have a really big velocity, which is a longer arrow, a longer vector, because it has a higher magnitude. And the magnitude is basically just like the value of the speed. So if your velocity at the beginning is like 10 meters per second, like I said, if each like square or whatever is like a meter, then it would be 10 long. So yeah, that's your like y projection essentially on the right hand side. And that's what you're seeing on the bottom too, how all of these vectors are the same length is because the velocity is not changing in the x direction. Okay, that being said, projectile motion. Basically, the equations simplify. So your velocity along the x-axis is equal to your initial velocity, which is marked as Vx naught, or V subscript x0. Just normal convention to say x or V naught, Vx naught. And then same thing with the x equation below. And then the motion along the y-axis gets a little bit more complicated here. It's just the same thing. For now and for coding in Python, you can just kind of plug and chug. I'm not going to do the derivations for those. Just Vy is like your velocity in the y direction, or the velocity y projection on the y-axis. And yeah, y is your position, y naught is your initial position. Vy naught is your velocity at the initial position in the y direction only. If you're confused by all of the different terms and the different terminology, I suggest making a table and writing everything out and going, okay, Vy naught is the velocity in only the y direction at the starting position. And doing that for all the variables, and that'll help you see things a little bit easier. Any questions on this? Okay. The first example I had was writing the equations in Python. So the kinematic velocity equation in the x direction, the kinematic velocity equation in the y direction, and then the acceleration equation. So that would essentially just be like these guys. So if we were to write those, how would we do that? Let's just go back to here. That's not what I want. Okay, so the first one, kinematic motion equation in the x direction. So here, we see that x of t is equal to x naught v naught x times t. Let's start with that. So x, and then that's x of t. You can do x underscore t if you want, but it's going to interpret parentheses as like taking in a function. So you can't do that. And then also just like as a side note, because of the parentheses, you can't do like 2 times 2 in parentheses. It will not interpret that as multiplication. You have to put a multiplication sign if you want that. So that being said, we'll do x naught. Make sure this is correct. X naught plus v naught or vx naught. We'll do 0. Times t plus double checking a x divided by 2 times t squared. And then I'm just really paranoid about parentheses and it not interpreting what I'm writing correctly. So I put this entire last term in parentheses. It does have PEMDAS written into it, so it'll understand it if you do like this term, the Vx naught times t. But this one is a little bit more complicated, which is why I did it. Any questions on that? So that was, I think like part 1. We did cover this briefly earlier, but I'm just going over operations again. Probably pretty used to it with like typing in like Google Docs, slides, whatever. So we can do the second one is the exact same thing, but in Y. So it's gonna be in the Y direction. While I'm typing this, are there like any questions from online?
That's.
The project? Yeah, I'm gonna get to it. Okay, I'm not gonna do the last one, because I think that we get the gist of this. If you want to do practice, you can do the acceleration equation. That's fine. Okay, that was the first one, and then I do have a second example prepared if we want to do that one, or it's up to you guys if you feel you would benefit from going over just like more live coding examples, which is what I've been doing. Or if you want to do another one, which is like elastic scattering. So it's like if you have the really classic equation of like 2 billiards balls and they're both moving and they collide, and like plotting that. Do you guys want to do that? Okay, we'll do that. And then we'll get on to the project and I'll explain it quickly after that. Yeah. So the elastic scattering is, that's not what I'm. Take a like 2-second break. While I pull this up real quick, because I don't want to show you guys the answer.
That's just the phone. We just have to see the whole thing. High school. Can't have it next year. And only we were. Well, one of the two start Michael seems to be. I think we like want to go to Collins. Makes it okay. One goes to college.
Okay.
Oh. Showing that you don't only take. You don't know the way, you can't make it like that.
Okay, so this is. Sorry, very short break because we are running out of time now. So this is the Google Colab that is already in the student folder. You should be able to see this one. It says student elastic scattering example. So yeah, we've already imported all of our packages. So we're doing NumPy, we're doing math, which is a package. And then we're doing matplotlib.pyplot as PLT. That's just for plotting. Yeah. So if we have two different balls, we'll say one is red, one is blue. Then X0B is going to be the positions of them before B, which is the collision in a list. So these are going to be the initial positions. And then we will set, sorry, I just want to make sure that the answer key is the same when I post it. So X not red is going to be 10, and then X not blue is going to be -10. And then the array is going to be just values from those two initial positions. So VB, which is going to be the initial, standing for V before, is going to be the velocities before the collision. So that's going to be -1.1, -1.8, and 1.8, not negative. So these are going towards each other because one is negative, one is positive, which means they're going in opposite directions. Does that make sense? We're on our number line. Okay, awesome. So our VB array is going to be from VB red to VB blue. So there we go. That's our velocity array. And then our masses are going to be 1 and 3. And then let's not worry about this here now. So we're going to have some combinations. So we're going to do M sum. These are going to be useful later. It's just going to be MR plus MB. And then we're going to have M difference. And then it's going to be MR minus MB. So we'll just say useful combinations for later. And then remember to always run your cells. Otherwise you get errors. That shouldn't be there. Okay, awesome. And then we're going to do our mass matrix. So recall a matrix from earlier. It's just like a square of numbers, basically. So mass matrix equals numpy.array. So we want an array with the different mass values, the difference of it. So we're going to do this, and then we're going to do mdiff, which is what we just calculated earlier, divided by msum. And then we're going to do 2 times mb over msum. Okay. And this is just like from a physics equation, so don't worry about it for now. Yeah, added an extra parentheses on accident. There you go. Okay, awesome. So yeah, you can see that the parentheses change colors when you close them and whatnot. So we'll run that, and it's not happy. Hmm. I think we're missing a parenthesis. Maybe. This one. Okay, there we go. There's the parentheses. So now that we have our mass matrix organized, you can see, this is the same format as earlier, just with different values in it. So we have our NumPy array, which is our first blue parentheses. Then within that, we have a tuple. And then we have our first value, which is going to be a mass value, and our second value, which is another mass value of our second one. And then, oops. From here, we want to print it because we want to see what we did. And that's going to be, yeah, what we expect. So 0.5, 1.5, 0.5, 0.5. Does that make sense? A little bit. Awesome. So we're going to go back to creating another list of the final velocities. And we're going to use the mass matrix, and then we're going to use, okay, so dotting is basically just multiplying, but it's like each of the individual components. So we have the dotting of the mass matrix, dotting times the velocity matrix, which is from the conservation of momentum equation where you have m times v. So when the two billiard balls combine, you have the mass from this one, the mass and the velocity from this one, and then you have the mass and velocity from the second one. So MV1, MV2, you have both of those separately, and your momentum equation is usually, once you simplify it down, it's like MV1 plus MV2 equals, it's MV1, MV naught 1, MV naught 2 equals MV1 plus MV2. Does that make sense? So you have your initial momentum, and then you have equal to your final momentum. That's assuming that no energy is lost due to friction or anything like that. So that's why we're multiplying the two. And then if you want to print those two, we can do a couple print statements. So this is where it is not happy. I didn't run any of my code before. Again, this is why I said to run your code like 3 different times. Okay, now everything's happy. Okay, so if we want to do a print, we can just say print velocity of the red marble after collision. So that is one long string. And then we can put a comma and it's going to print the next thing, which is going to be a variable. So we're going to say VA, and then we're going to index it. So it's going to be 0. And then we're going to do another statement. So it's going to be basically the same thing, but just with VB, or sorry, VA, and then 1. I'm getting ahead of myself. And then if we print that, awesome. So sorry, this one should say blue. So the red marble after the first collision, the velocity of that is going to be 3.25. And then also if you wanted to be even more detailed, you could say meters per second. And you just put another comma and you make another string and you say meters per second, and it'll print all of those. And now you have units. You can just, yeah, play around with it. You can do print strings. There's a helpful tool called an F string, if you ever see that, which is the same thing, which is just going to be velocity of the blue marble after collision. And in this case, you can just do curly brackets and you can say VA, and then you can do 1, and you can close your string outside of it, and then you can say meters per second. That allows you to do everything in one string without doing the commas like above, and it should work. So the curly brackets just say treat this as a variable and assign it to the previous value that was assigned to it. instead of reading it as a string, because if I didn't do that as an f string and I just did that as a normal print statement, then it prints VA index 1, and that's not very useful. So that's an f string. Just a side tangent. Okay. So if we want to continue moving along with this, then let's see. I just want to make sure all this matches. Okay, then we're going to make another function for the position of it. And that's going to be using our beginning velocity or position, and then our beginning velocities as well, and then a time function or time array. And we're going to have. So this equation is essentially just our x equation from the slides. Sorry, I'm trying to find my slides. From the slides on here, it's this guy. It's the same equation that we're using over here. If we run it, awesome. There's our function. And then we want the time of collision, which is going to be, we have a marker for that. So it's going to be x naught b index of 0 minus x naught b index of 1. And then we'll do the b index of 1 divided by, and then the b index of 0. So I'm going to put parentheses around these so that, just so I know and have peace of mind that it is in fact recognizing them in the correct order. And the difference in beginning times and positions is going to give me a collision time, because v is just x over t. So if you have x over t, then the bottom one flips, and then you have your time, because the x's cancel out. There we go. Did that make sense? Is everyone following up to this point? Okay. This is like a pretty classic physics problem. So yeah, if you're confused, there are tons of examples online. And then we can do another print statement for this, just to be thorough with this. We'll do print. We'll do another f string. We'll say collision time, which is what that equation gives, and then we'll say the seconds. So there we go. So clock time at the collision is going to be 6.89 seconds, give or take. Okay. And then we'll do we want to find the collision position now. So that's going to be x naught b plus vb times collision time. So this is saying velocity at that specific time and the position. This is the same equation that we just saw, but with different inputs for different times and different x values. So we can run this one, and then we can also yeah, I mean, it's a collision position. We don't need to do another print statement. So collision position, awesome. And then we can make an array out of that. Actually, it's already in an array. Sorry, read that backwards. So we're going to do another list of sorts. So collision time over 100. We want a T1. I'm just working on plotting it right now. Actually, I have a couple minutes. Okay. I will get to the project. It will be homework. Sorry. C 0, collision time, and then step size. So the syntax of this is always start, stop, step. NumPy.arange basically makes a range of numbers. between the start, stop, and the step is the distance between the numbers or the separation that you want between the numbers. So we're starting at 0, we're stopping at the collision time, and then the step size is going to be the step size that we determined, which is the collision time divided by 100. So we want 100 different intervals before we get to the collision. So it's going to give us 100 different position and velocities of each one of the different balls before we get to that collision time. So then we're going to do T2, and it's going to be numpy.a range. Collision time minus the step size. And then 2 times collision time. And yeah, very similar. And then we're gonna do red position. We're gonna create an empty list. I'm just working on plotting it at this point so that you guys can have a visualization. So when you want a value to be stored somewhere, you can create a list beforehand, and that's what I'm doing. So I'm creating a bunch of different lists that will hold information in a second so that I can plot it. Because we want to find the position at a specific time, and all those positions using the times that I just calculated for the step size and collision time, which is T1 and T2, is going to be used with these position lists in order to find where they are and then eventually plot a visualization of what it would actually look like. So actually, I'm going to run out of time for this. I cannot type fast enough. So I can post this later, or if you want to work through this also, that's totally fine, but I can post the answer to you later. In terms of the project, let's go back. In terms of the project, this is going to be project 1. It is 1 question. There's 4 steps. Don't freak out. You're not being graded. It's for you to learn. It's basically just going to take you through projectile motion. You're going to derive some of the equations. Like the first one is write a function for a 1D position as a function of time and initial conditions for constant acceleration. So if you saw the 2D equations from earlier, they are 2D, but they are for constant acceleration. So you can derive that knowing that velocity is the derivative of like dx over dt. Excuse me. Or derivative of position over time. And if you're like super confused, don't be afraid to use the internet after you attempt it. Yeah, step 2, it's very similar, right? A function for 1D velocity as a function of time and initial conditions. Very similar. First one is position, second one is velocity, and then you're gonna go through a couple different things. You're gonna write some code that's gonna be basically make the plot of a projectile. So it's gonna be this. So it's just a quick little parabola, but it's in the context of physics and like throwing a ball. So that would be holding a y constant, which is going to be gravity, and then ax equals 0. So that's what I was talking about with this plot. So ax equals 0, ay is gravity, and then writing code for those. So xy, bx, and then by to derive those values. And then step 4 would just be write code for plotting the y as a function for x and some initial values of x, y, bx, and by. I know that was really fast. It's 1 question. Don't worry about it if it's super confused. I think we might try to go over it next lecture, but it will overlap. So don't be too worried about it. But yeah, if you're concerned about plotting, it's plt.plot, x label, and legend. This is what I was trying to do. I'm going to post these later, but essentially what we're doing is it's going to plot this. But the general like function of it is plt.figure, plt.plot, and then plt.show. That's all you need to make a plot. Which is also very readily available on the internet, but I'll make sure that's in a note somewhere with the course materials. That's it for today. I know it was a ton of information, but you guys did really, really good. Thank you so much, and we'll see you guys next week.
All right.